Right. So in this what happens is let's say this is that's a homopolar. So that it will end up having the current flowing in the same direction. Okay. It will flow in the same direction. Right. So the homopolar is the disk. This is our north pole. This is our south pole. Okay. Now this is moving that way. At this point, if you apply the Fleming's right hand rule, because it's motor, it's because it's generator right hand rule. Okay. At this point, this is the term. Okay. Right. The term, the field. So we have the current. The term is the motion. You have the field like that. Okay. So my term is showing where this one is going. So the field. Okay, the right hand rule. Okay, that's the generator. Okay, and then that's the current. Okay, so I have my current that will be flowing. Let's say the actual point flow, whichever way it goes this way, that the current is moving that way. There's the motion. Okay, current is moving. Now, if this at this point this is going that way. At the end, you have the current also moving, so that way. So at the end, it will be going in the same direction, and this is picked up. Okay, this is picked up. This is picked up, and then you have the current going that way. So it will end up going in the same direction. Right. You can look at it. So that's the polar disk. Okay. Right. So to give you a steady current. Now let's look at the Sabio. Now before let's look at the Bio Sava law. Now according to that law, if you have this as your wire and then you have a point here, it makes this angle alpha. Okay, here's the current conductor. Okay, so it has a field effect here. It has a field effect here. Change in B. Okay, now the relationship change in B is proportional to the current that is flowing through this, the length of that, and then the sine of the angle. And of course, inversely proportional to the distance, which is R, between the 2 points. Okay, now if you apply that for, let's say this is the curve. So from this equation, if you let this be proportional to that, okay, you realize that this sine here at every point is 90 degrees. Okay, sine becoming 90 is 1, so it becomes 1. Okay, so and this you're going to sum it along the circumference. If you sum it along the circumference, okay, so that will be from your change in L is going to your circumference, which is what 2 pi r. Okay, right. So that will come into the equation for L, okay, and that is going to cancel. 1 r is going to cancel that one here. Let's put this 2 there, okay. That is going to cancel 1 r there, okay. And then you shouldn't forget we have constants in for if we take off this one. So as you sum what you're trying to do is you find an equation relating this with B, and then you sum from where from 0 to 2 pi r. You do that, you put that in the equation in place of L here. Okay, so you get your L as a variable. You sum it, you integrate with respect to your L here. And then that is going to give you the equation, right? So of course you are multiplying by the end here, right? Just remember that the constant here, the constant for this equation, okay, becomes mu over 4 pi. Mu over 4 pi. Okay, so that is why we have 4 pi in the equation. So mu over 4 pi. So if you do the substitution proper, you're going to get B. If you integrate this, you're going to get B is equal to mu over 4 pi. Then this would come out to be your L. Okay, I I sine alpha 1, these two. Right, so from that onwards, I think the next thing that we can do, this is what I mean. From here, you can get this. Change in D is equal to what? Your mu over 4 pi times your I, change in L, sine alpha over R squared. Okay? So once you have this one, now you have this and that. Okay, so you can integrate this part and integrate that for depending on the equation. So for here, the L becomes what? 2 pi R. If we have number of terms times n. Okay, so you integrate for that one, and then this will give you come back to this equation. When this is the coil and then the distance away. Okay, now this distance away here, okay, has an angle it's making with this. Okay, has an angle. Now if we want to find the field, each of these parts contribute to this field, okay, E. Okay, then what will happen is, if you do that, so this, let's say the force has a certain angle, which is beta. If you do the calculation of this, and that will be the same. Okay, so it's normal, the normal part to this angle, to this part of the curve. Okay, you get it, you find it, resolve it, you get the normal part. Okay, now you do the same thing. That is for this half. So you do the same thing, you get this half, and then part of it will be here. So part will be here, part of that. Now if you do that for this half of the equation, you get half. But you do that for this half. So this and that will cancel. Then you will left with this one alone. So see that it will come out to be your what? Sine beta. This sine beta. Okay, times the total length. Okay, total length of this one, which is your 2 pi r. And then if you put that in, put in the constant in here, you do the summation. Of course, A becomes the radius. You do the summation, the radius for this, that's the distance to the point here, and then this as your r. Okay, distance to the midpoint. Okay, or the distance to your r here. Okay, and then that will give you the answer. But let's look at this one. Okay, so this is your R. Okay, this is your A. Right, so by that substitution, you do it, you arrive at this equation. But this one, remember, we are summing for B in this case. Okay, it will only be sine B, but this is the right sine B in this calculation will give you that equation. Right, because we have to resolve it kind of for this part and then for that part. Right. Okay. If we look at so that is for this equation. Let's look at this one. When it comes to this one too, so the various you need to have the components. Okay. So here we are making use of the angle rather. So that if the angle, as the angle opens up from the limits, let's say between pi, the limit up to 180. Okay, that is pi. Okay, from 0 to pi. That will give us B here, because we are looking at the point. They all contribute to this point. So the angle that is being made here, of course, once we are looking at it, we are looking at the angle that each of these units, the point here makes with this. Okay, so one point is here, another point is here. Okay, so until it comes to 90, which will be half of pi. Okay, so this opens up to 180, which is pi. And it's so from that angle to that. So we can do that until for a very long one, we are approaching almost 180. Okay, so you do that and then that will come up to this equation. Now the same thing can be applied for here, where we have the conductor. As long as this is the point, this is the angle. Okay, so here we substitute in the values. We sum from 0 to pi because you're going to have up to 90 degrees. So as you go further, each point, this is the point is given. If you come here, at this point it becomes 90 degrees. Okay, then you have the same half on the other side. Okay, and if you go, keep on going. Okay, angle until infinity. So you have to sign as you are going. Remember, this angle is increasing. It's increasing to 90. So this will be decreasing to 0. So from 0 to 90, then you try to find the, because you are looking at an angle, try to get the L in terms of angles, and then that will work and then come out to this equation. So these ones you can try your hands on, you work it out, it will come out to this kind of equation. So what you should remember is you get rid of L and then convert it to angles so that you can find the angles. Okay, right? The same thing here too. You get rid of L, get it in place of beta, or the angles that will be expanding, and then use it to work for the limits. Okay, here you get rid of the radius, the length, right, becomes the radius. Okay, that's what you used to do. You substitute in, and then you are getting your angles, right? Here you make use of your L's, okay, not the angles, right? The same thing, the Ampere's rule, it says, it's a little complex beyond us, but there is a given rule that your flux density over the permittivity of vacuum, okay, if you sum that one over this length, the total length that you are dealing with, let's say it's a circular, the total length of this, you sum it up, you get this value, okay? Right, so that's the general equation. We can use it to derive these ones that we have discussed. So that will bring us to the end of the section on Biot-Savart. You can look at it and then try your hands on. So one, you try to connect this and then the length, where possible. And other times where it's not possible, you connect, you find the range in terms of angle, okay, and integrate, okay, especially for these ones, okay, these ones. Then this one, okay, when it comes to this one, you can emit the length and then the angle comes in. So the angle, your angle, okay, then of course here there's no angle, for it's the same angle throughout. So the length becomes the variable. We use the variable together. But here the angle comes in. The length is limited. So angle can give you the limits, okay, and you can use that one. So all you do is you look at it, whether angle is okay or length is okay, then use that one to derive the equation. Right. Now let's look at the AC current. AC current. Let's assume, so this is the AC current, okay? It's connected to capacitor. Like that. Now what happens is, first of all, the current goes that way, and then in the other half comes that way. Okay, so it's that, and then opposites. So this is the current. Okay, now let's assume this voltage is given, voltage of the mains is given. Now this is a capacitor. Okay, so when it's connected to the voltage, charge still start building up, okay, to create the voltage. So you can intuitively say that the charge comes before voltage. In other words, current means voltage, okay? So let's assume at any instant, because this is changing, we can find the instantaneous. So at any instant, the instantaneous voltage will be what? We know this is similar to the circle equation that we did, okay, where we have y and then this is time, okay? So at this angle, the current is here, is going. Okay, so it's changed along this, okay? So at every point we have a certain change. We can link this one with voltage, we can link voltage against time, and then in that case we're going to have this sine, what that is, the connection will be sine theta is equal to what? Opposite, which is y over hypotenuse. Hypotenuse becomes b, okay? So that it is b sine theta, okay, is equal to y. Now, if y is the voltage, okay, because we are dealing with voltage, this should be voltage, okay. this y is the instantaneous. This is the instantaneous voltage over that's the instantaneous opposite over hypotenuse, and then this is the radius, which is v. But at the point where this gets to the maximum, v becomes the v max, so we can say v max. So that from here we can say that v instantaneous is equal to v max sine theta. V instantaneous is equal to v max sine theta. But we know theta, for one complete revolution, theta is equal to what? 2 pi. That's one complete revolution. Theta is equal to 2 pi. Okay? Or in other words, too, we can say that we know time or the period is equal to what? 2 pi over omega. Shouldn't forget that one. Period is equal to that. Now this is radius, the radius in radians, okay? This is what you have, radians, a complete radians. If you take 360, it is 2 pi, okay? And the period is this. Now, period is also linked to frequency is equal to number of times over t. So for one revolution, there is 1 over t. So that this implies that t is equal to 1 over f. Okay, so this is the same as saying from here. It's the same as saying 1 over f is equal to 2 pi omega. Okay? But remember, we can get our, so this is what we have here. Remember, omega is equal to theta over t, which is the same as terms of, that is the angle of rotation. It is 362 pi over capital T. Okay? And of course, we see that t is equal to 1 over f. So this will mean, this is the same as saying that this is equal to 2 pi over 1 over f, which becomes 2 pi f. Okay? Now, from here, from this point, what do you think? So it means from here, theta can be said to be equal to omega t. Okay? Theta can be said to be equal to omega t. Right? And then we have said omega is also equal to what? 2 pi f from here. Okay? Omega is equal to 2 pi f. So we can put theta to be equal to what? 2 pi f t. Now this is what we are interested in. This is what has been, we can put here. Right? So that we can say that from all that we have done, we can say that V instantaneous is equal to V maximum sine 2 pi ft. This is the instantaneous V. Now first of all, get these values in AC well. This RMS means the root mean square, and it is equal to the square root of the current. So the current squared over your number of watts, that's your 2. Okay, so what is happening is, let's say I have what you call the initial i's, which are being squared. Okay, now I want to find the mean, which is, if I want to find the number of the mean, because it's some can be negative, some can be positive, I'll square it. When I square it, I have to find the mean. The mean is divided by 2, because we have between 2 from 0 to maximum. Okay. And then when I've done that, I have to find square root of that, and then that will give me the root mean square. But of course, so this will come to what? I over what? Square root of 2 is equal to the root mean square. Now the root mean square can be taken to be the average, and then we can work with that. Okay. right? And the point is we can also have the maximum I. Let's say I maximum or I naught as a maximum, because this is rising and going down. So you can have this as the average, more or less like the average, and this is the maximum. So those points will be used in the equation so that you note them well. Right. Right, so that is that for this capacitor. Right, remember this is you can also look at it this way. This is actually the the maximum current that we are dealing with. Okay, the maximum, and there is a root mean. You can just make it IR in some books. Okay, so this is the maximum. So you can be asked to calculate. Okay, so let's now with this formula in here. This is the one that we are interested in. If we have this, we also know that Q, that's the charge that is going to be built up on this, is related to capacitance. Okay, Q, we know from the definition, capacitance is equal to what? Your Q over V, which is the same as what Q is equal to CV. Right, now this is what we have, our instantaneous charge, the capacitance is constant, and then instantaneous what? Instantaneous charge, instantaneous what? Voltage. Okay, right, so this charge can be expressed in terms of current is equal to the Q, the R, and the T. Okay, right, so we should also bear in mind this one. Now let's see from here. You can say that Q is equal to C, which is a constant. I'm going to put this one there. Vm sine 2 pi ft. Now, if we differentiate this part, find the Q, the T, differentiating with respect to T, this is going to be this C Am sine 2 pi ft all over the T. So that this we know is an expression for I, current. And this is a constant, so constant comes out. This is also constant, constant, okay? The sine 2 pi f t dt. Okay? Right. So if we differentiate this, what are we going to get? So I is equal to, if we differentiate this, we're going to get what? Cos. So C V M cos, of course this is the constant will always come out if you have it. So we're going to have your constant as it is here. So just as when you differentiate anything, what you are differentiating with, the coefficient comes out. So the coefficient here, the coefficient which is this one of t comes out as 2 pi f, and then we have what? Cos 2 pi f. Okay. So this is the equation. So you see that the equation for current is cos. You know the normal equation is this. This is cos curve and this is sine curve. Okay. So it means this is the I and this is your V. So it means I is leading V for the capacitor. The opposite is for the inductor. If you have the inductor, you get the opposite. So if, let's say this to my inductor, okay, then I'll have the opposite, okay, the opposite is what is going to happen. So in that case, I'm going to have my I, which is going to be Im sine 2 pi ft. Okay, this is my instantaneous I, okay, right, so if you work it out, just like we did for the I value, okay, you will come out to know that voltage leads what? Current, in the case of the inductor. Sorry, in the case of the inductor. So that is one thing. Now, having done that, if we know the principle, we can now look at the equations that are derived. So straight away, I'll go to where we have the three components in. So let's look at the series arrangement of capacitor. Let me make it. Then we have a capacitor, we have a resistor connected to the AC mains, okay? Something like that. Now, if we have this, how do we work things out? So here we will know that the voltage here will be different, voltage here will be different, voltage here will be different, but they will have the same current through them. Okay, so let's see what will be the effective voltage. The effective voltage must be equal to this one. Okay, the mains. Okay, so what will be the effective voltage? How do we get it? And these, remember, these have become vectors, more or less vectors. So we have to look at them well. So in the case of, let's start with the case of the capacitor. In the case of capacitor, let's assume this is the resistor. Okay, this is the resistor part. Okay. In case of capacitor, we say what? Current leads voltage. Okay, so current can be here. So this will be IC, is leading voltage. Okay. Now, in the case of the inductor, we say voltage leads current. Okay. So voltage is leading current. So this will be I inductor. Okay, let's put the inductor here. Right. So this is it. As for the resistor, there's no, it's not causing, it's not alternating. So it has a fixed point and it goes like that. So if we already know the current is the same for all of them once it's full, so we can forget about this one and then look at the voltage rather. Let's look at where each one the voltage will be. So let's look at it from this angle. So, right, because the current are the same, we can't use this approach. Let's look at it from this angle. Now the current is the same, so we can assume this is current for all of them. So if this is current, in the case of a capacitor, current is leading voltage. So what do you think voltage will be? Current is leading voltage. Okay, current is leading. Because it's the same, it is C, it is I, and it is R, the same thing. Now, because current is leading voltage in capacitor, voltage will be here. So voltage for capacitor is here. Because current leads it. Okay. In the case of inductor, voltage leads current. Voltage leads current. So voltage for inductor is here. Right. Now for the resistor, the voltage is in the same direction as the current. So this is the resistor. Now how do you get the resultant V, the V for the effective V for all of them, which is equal to this? So that V will be equal to what? How do you get that? Now, if you want to get, these are vectors, so you can't add them straight away. So it should be the difference between V, I, and then V, C, the difference, okay? Let's say it comes to something like that. So this is the vector. Then we can find the resultant, which will be this V. So this V, let's say, given by an angle that, okay, or that's by this point, okay? We can say that here, assuming this will be V I minus what V C, okay? You can use the Pythagoras theorem, okay, to find if this is V and this is that, okay? Because this is V I. We can say that V squared is equal to Vi minus what? Vc all squared plus Vi squared is equal to that. Okay. Now, when we have this expression, we can then put the values in there. We can put the values in there. Okay, so this one, the general V, okay, would have been that the same current will be through it. The resistance will be the overall impedance. Okay, the overall impedance. Let me just make it the overall impedance. Okay, so impedance times impedance. Okay, now all this has been squared. Or in other words, you can just say that let's make it V is equal to the square root of this. Okay, so at this point, this is the equation I want us to look at. Okay, now from this we can substitute for the values that V is equal to IR. You can put them in and then see, but remember I will be the same throughout. Okay, so here let's say resistance is going to be X L X C for inductance. Okay, so we can make it VL, so VL, okay, VL, right. Remember when we square this, whether this was subtracted or this one, it will just come back to the same. Right, so in this case, the overall Z, okay, the overall impedance is Z, okay, so we're going to have what? I Z is equal to square root of what? This is going to give us XL, I XL, minus what? I SC squared plus what? I R all squared. Okay, right. So, and that is going to give us an expression. So Z will be equal to, of course, let's see if we can bring the Z out. Oh, that is the equation for now. See if we can let this one come out. So from here, let's see what we're going to get. Let me just go back here. So from here, we're going to have RV. This we said is going to be so let's say V squared, assuming we are from here, the same thing. This is going to give us what? I XL minus I XC squared plus I squared